Okay, good morning. Can you hear me?
Good morning, doctor. Yes, we
Good morning,
can.
doctor. Yes, we can hear you clearly.
Yes,
Okay.
doctor.
Okay, thank you. So we can start. So last week uh, we have uh, finished over here that we have taken particularly the uh, about the asset management, journal intro, and the code and standard. So whenever we were talking that asset, which is a building, bridge, equipment, or plant, right? So the technical asset management, as we have discussed, we have to look that asset is at a threat of the external environment, right? So the external environment, one of them is the which is exposure condition in the surrounding. So one is the most important is the temperature, right? We are having, if we will get the scenario of the whole planet. So at the moment, somewhere there is sub-zero temperature and somewhere there is a hot climate. So in that sense, that the asset which can be subjected to external causes and internal defects, right? So the external, which means that we have to design the asset, equipment, so or a bridge, or building, or plant structure. So it is to be subjected to the expected environmental condition, right? And there are also the internal defects, right? So type of requirement. So functional requirement, what is the input and output internally, as we discussed, that efficiency of equipment is important if we are talking production line, right? So there are internal defects which may cause the output is lesser than the input, processing, error handling, right? So those are uh, in general that can affect. There are also non-functional, as we say, physical environment, equipment location, multiple site, interface, user and human factor, right? Which are also who are the user, their skill and level, meaning to say different people operate differently, right? So some are following SOP, standard SOP 100%, some are not. So those are also because sometimes that's why we include in maintenance engineering the skill and the skill improvement. Let's say new equipment which is being replaced by an old equipment. So new equipment with AI functions and all. So without having training, understanding, so the input and output may be suffering, right? So asset integrity will be. So in general, this slide is just showing that for integrity and management of asset, so we have to comply the maximum to the functional and non-functional requirement for maintaining the asset. So in general, uh, from the requirement, functional requirement of a structure or equipment, anything is designed to resist the most unfavorable situation arises during the intended design life and supposed to meet the criteria of strength and stability, right? As I think last week we will be strength, which means that the whatever equipment or structure, it will be subjected to external loading. So that external loading, like this is uh, shaft. So there will be pulling action, pushing action. So that might cause the elongation, cracking. So the material properties and the geometry of the shaft. First of all, it may bend because of the poor geometry, so it is not stable. Second, it can crush, it can crack, which means its strength is not sufficient, right? Which means some design error. The shaft diameter to be bigger than what is being designed, right? So, meaning to say to perform its function, so the asset to be complying to the strength and stability criteria. So strength and stability. So this is the design requirement. So particularly the design condition to be fulfilled during the entire life of the structure. For example, uh, as how the design specification are being deteriorating with age, right? In pipeline engineering, right? So the pipeline, when getting older, if not maintained properly. So when a new pipeline you are designing, for example, a gas pipeline for maximum allowable operating pressure of 200 bar, right? And for that API or any standard, you design API 60 X65 steel pipe, and you come up that because the pipeline design is governed by the wall thickness of pipe, and you come up that the thickness is 20 mm. For example, X65 pipe for 200 bar pressure, you design 20 mm thick, right? So uh, with the service service of the pipe, service life. So some internal corrosion spot has been occurred. So let's say 20% of the pipe thickness have been lost due to corrosion, and if it is not being maintaining, so your design thickness was 20 mm. Now the thickness, the functional thickness remain 18 mm. So the operating pressure, which was supposed to be 200, so maybe it has gone down maybe 170, maybe 180 bar, right? So which means now either your working requirement are gone down, or you cannot operate at 200 bar, or you have to upgrade, right? So that is the resistance to the weather, strength and stability, right? Which can comply. Durability. So again, as we say, one of the reason where strength loss, which means due to durability effect. Corrosion is a durability effects, right? So, which means the good maintenance, that by doing so, continuous inspection, and not only inspection, the evaluation of inspection data continuously, that will help us to predict the losses, right, or rate of losses. So that that will be giving us the good maintenance cycle. So we can delay or we can ignore. Fire safety, right? This is also because the fire trigger can also cause resistance to passage to heat, resistance to the passage of sound. So those are the trigger mechanism or trigger criteria which will affect the assets, right? this is just that's right. So, for example, previous picture like this flooring, if we are getting this example. So, what industrial or commercial flooring? What are the functional requirements of a floor slab at which these people provide a flat surface? If you will go see back, strength and stability, meaning to say that is one of the requirements. It will not be uneven, for example. It should be a flat surface, people, because the uneven or bumpy surface, so it will be affecting the walking of the people, like corridor or the big ground where walking is there. Second, this tiling and the floor should not be cracked, it should not be damaged, right? So it should have sufficient strength, right? So strength, stability should not buckle, durability and freedom from maintenance, right? So which means the good maintenance, it will delay the good data, good prediction. So quality control that will make it delay the next detailed inspection cycle. It can support load, right? Whatever, if it is designed for 200 people, so it can support load. In the event of fire, it should not be damage resistant. So all these parameters, it should comply the floor design, right? So if it is in any floor, industrial floor or whatsoever. So from this example, we can say asset management. If from there we can craft the definition, systematic and synchronized activities through which organization manage their asset optimal and sustainable over their life cycle to accomplish organization strategic plan. So one is systematic, meaning to say in sequence, right? So what and synchronized. Synchronized, which is relevant to one another, right? So, and relevant to the the previous slide criteria, durability, right? Strength criteria, right? So, all those things. So, that is the broad, concise, and comprehensive definition. So, asset management, there are few things, so which will come asset in term again indirectly integrity, right? So it which means that the asset, whether equipment, efficiency, all, so that is depending on to the integrity. So in asset integrity management, so asset management is a broad which include technical and non-technical management, which means the human capital quality management, right? That will also come under the asset management. For example, the new skill of the equipment. Asset integrity is the technical assessment of asset to manage integrity over the life cycle of an asset. For example, uh, wherever uh, integrity, we are managing the pipeline can is designed for 200 megapascal operating pressure, right? So we have to ensure, we have to manage that for next 20 years. So the pipeline should be qualified for 200 bar operating pressure, right? So that is integrity, pure technical, structural management. And overall asset management. So in that, because for the managing pipeline, you are doing frequent or at any interval of inspection you are performing pig. So the pigging operation, so where in asset management it include as the pig are being new versions are coming. So knowledge of pig is also important. So time to time the new pig high performance pig, intelligent pigs are coming into the market. So asset management requirement are that the pipeline of maintenance engineer must be sent for the training. So that is the part of asset management. But wherever we are talking asset integrity management, which is solely dedicated to the pipeline integrity, the strength of the pipeline, the capability that pipeline should be assured to, to resist the allowable operating pressure of 200 bar. Asset integrity, so is the, so we will come the universal uh, term is asset, under asset is asset integrity, and then asset integrity management, then asset integrity definition, which is ability of an asset to perform its function, which is 200 bar effectively and efficiently, which means continuously 365/7 as and when required through protection the uh, health, safety, and environment. Meaning to say, it is complying all the functional requirement, HSC requirement. So it is safe to run at 200 bar all the time during its service life. That is the integrity that asset is capable. So whenever in this term, and all of you, if you are working in some companies or you have experience, so in general, time to time, we have to do the inspection, test, and NDTs on that, right? And through that, we are getting plenty of data, right? So this data uh, we have to go. There are one is the journal analysis. Look at the data train, right? So some shortcut method sometimes we use, right? With in many industry we use that you are monitoring something like pressure monitoring. If they say, okay, that pressure data if it is exceeding to that number, some magic number, so you have to change this thing or something. But that if you would like to assure the integrity, so you have to analyze the data. You have to do some analysis and calculation through the data, and you can get what is the mode of data, what is the statistics of the data, and on that basis, you cannot only know the condition at this at the present time, but from data you can predict the mode, right? You can predict, for example, corrosion data. From corrosion data, and you will look at the past corrosion data, so you can estimate, you can predict that how long it will take that the pipe corrosion will decay the pipe, that you cannot operate more than 100 bar, right? So those kind of things, because in detail analysis of the data, so that will save your uh, inspection, it will save your money. So all these exercises are uh, fall under appraisal. So in the context of this subject, uh, it means condition assessment, evaluation, of a structure and or equipment that assists to know the weakness and strength of the asset, right? Sometimes, like the detailed methods of analysis, it will. So the asset appraisal is a way in fitness for service certification, right? So in general, fitness for service for this functional requirement is for 10 years, what we call warranty or guarantee. In other words, it is the structural health monitoring exercise, right? It is same thing like human being that determine the integrity, reliability, right? How reliable is that? So the fundamental principle of asset appraisal include to determine the integrity, reliability of a structure or equipment by performing the detailed health monitoring exercise. Health monitoring involve both testing, getting data, and data analysis, right? And data analysis and data evaluation and result conclusion, right? So that is the whole sum of exercise, which like in reliability of structure or pipeline reliability, where you will be learning those techniques, right? So to determine the risk level and probability, and on that basis, you can estimate the risk by estimating the probability of failure, their likely consequences, so that undergoing a big exercise, right? It is not appraisal, it's not just that if just you are complying some magic number, right? But without further, so that magic number will give you the condition of today, right? But you cannot, without detailed analysis, you cannot predict or you cannot find the reliability of next few years, right? So to determine the extent and type of maintenance needed for an asset, right? So here, like this kind of olden structures like pyramids of Egypt and all, which are still, you can see some 1,000 years old structures are still there, right? So which means that integrity is a term which refers to the quality of being whole and complete, meaning to say they are not disintegrated, still they are complete and wholesome what they were at the time of design and at the time of application. As I'm referring you, the pipeline. So when it is at this time is also offering you the same conditions, the same performance, what it was desired at the time of the design and planning. So which means that the integrity is maintained is at higher level. So that is integrity is basically a technical term as we are talking assessment and all. So that exercise of data analysis, risk estimation, so that is called the structural integrity assessment, which is the approach to assess whether a structure is fit to withstand the service condition safely and reliably throughout its predicted lifetime. So philosophy is established philosophy behind the design of any structural component is to ensure that the strength of the material of which the component is made of is higher than the maximum applied stress in service. Meaning to say that the operating condition in engineering term, uh, we can say whatever functioning, so we are forcing, right? So which means that the induced load is should be less than the resistance capability, right? As this pen, right? So from my fingers, I'm trying to bend. So if that much force that I'm applying, and that I consider is the force which during operation will come onto this pen, right? You consider it is any technical part. But because at that moment it is circular, no crack, no bending, right? So, which means that the resistance of the pen is more than the operational load. But when I press much more, right, it will break. So, which means that the resistance of the pen is less than the operational load, which means the pen has lost its integrity, right? So that is the function of philosophy, that we can ensure that the strength of material, which is resistance of the material, should always be higher than the operating pressure. As I have given to you the example, if the corrosion spot is 20% of the wall thickness, so which means that the pipeline has lost its 20% capacity, right? Which means if the it will be running at the design maximum operating pressure of 200 bar, so its strength is not complying to that, which means the failure will occur, right? So which means that the strength loss will ask you to requalify the pipe for new operating condition, which might not be, if you would like to bring back your desired operating condition, which means in asset management term, you have to rehabilitate or you have to strengthen your pipe that will bring you back to the desired operating condition. So I think this slide and that slide have spoken. So more on in technical term, particularly if you are from engineering background and you have gone through the structure stress analysis, you have gone through the solid mechanics or strength of material, right? So what engineer does. So there are this, you are making a shaft, you are making a pipe. So you are choosing material and you are designing material. Meaning to say, if you have to design a pipeline for gas, right, which is to be transported maximum at 200 bar, as I've given, right? And that the hourly demand is, for example, it can transport 5,000 cubic meter per hour, for example, 500 cubic meter or whatever, some figure, right? So what do you do? So first thing that the pipeline, so first you have to do the flow requirement, and for that the flow of pipeline, you can estimate the diameter that will be 500 internal clear diameter of the pipe, right? So this gas which will be forcing at 200 bar or 20 megapascal, so that will applying pressure on the pipe wall thickness, and using the relevant design formula like API formula, you have come up that hoop stresses or tangential stresses or that stresses. So you come up the pipeline thickness is 20 mm. So that, and for that you have this 20 mm, you have chosen X65 pipe. So for X65 pipe, you have refer what is the yield strength, what is the ultimate strength, what is the ductility factor. So we play for in integrity analysis, so material and design. Whenever we are looking material, so we are looking properties and performance of material, right? So which means properties are the inherent built-in properties. Performance, the loss properties or the if not loss, right? Maintain properties. And design, we are working in possibilities and opportunities. Possibilities, which means that that's why we are putting safety factor. So sometimes we say, although we are saying it is 200 bar, but because of the error, human error or metering error, so if pressure fluctuate to 210 bar, right? So whether pipe will fail. So we are looking at the opportunity. We are looking, okay, oh, design factor, if API X65 pipe, so if the strength, yield strength is 650, for example, megapascal, but uh, the design strength, right? This is the material strength and the design strength, which is being considered 0.6 of Fy. So this 40%, right? So whether it can be complied through this, which is the safety factor, right? So meaning to say, whenever we are looking material, properties, performance, possibilities, and opportunities in this crisscrossing. So that exercise we are doing and checking, right? Material and design options, right? Phases and stages of asset integrity management, right? So these are the, uh, there are three main phases of integrity. Design integrity, which means where we will be looking at the bottom, which you can look concept, which means you are looking not only structural design, operational design. For example, uh, the client requirement is, for example, you design at running at this much pressure and the flow that much, because that you are providing or supplying that 100 cubic meter per minute or 10 cubic meter per minute flow rate, right? Which is, so that there should not be any wax deposition. So there will be clear 500 dia and so on, and the strength to be not compromised. So that is concept selection and design, right? So that will be complying, right? The design criteria. So that will be complying to the design integrity. And uh, technical integrity, which procurement, manufacturing, and construction, right? Faces hookup, installation, and commissioning. So that the SOP or guidelines, right? So the procurement, we generally consider it is just, but because the pipeline pipe segment, right? If you are buying 20% from one vendor, 30% from other vendor, 50% from three vendor and three different manufacturer. Like each of them are supplying pipe of FX65, but the uh, the nature, the number of chances of error and uncertainties have been increased, right? So that is not the good practice. A good practice, which many code and standards suggest, that say the majority or most of the same component from the same batch rather than same vendor, same manufacturer, same batch. So the reliability will increase. So manufacturing, how the code compliance have been done, and so on. Hookup installation and commissioning guidelines, right? And the third one is maintenance. So that the first two integrity until at the construction design to construction stage. The third one, maintenance integrity, which is at operation stage, where most of the people working in refineries, plant, right? So they, and in maintenance department, so they are performing in a way maintenance integrity of the asset, which means operating conditions and monitoring, modification as uh, the design conditions are if decaying, so we modify, or when we consider that it has surpassed the notional design life, and rather than the further modification might not be helpful, so we have to take the decision of decommission of the asset, right? So there are 6 stages of integrated design, procurement, right? From there we can, so which are in these boxes, so that the, these 3 stages come together, called the integrity management, which is the so for entire life cycle. So it is also called the, in sustainability term, life cycle management of the asset, right? So throughout the life cycle. So that linear diagram. So here the key element of asset integrity, as you can say, here this is in the shell, the nucleus is integrity management process, right? So which is, there are 4 quadrants. So each set, hazard evaluation, risk assessment, and integrity management planning, right? So there are action. So the action is that hazard evaluation, right? The fire hazard, for example, the weather hazard, and whatever, what are the available hazard, right? So hazards are always available, but if not managed properly, so they may become disaster. So based on that hazard, we can evaluate our asset and we find the risk. So that is integrity management planning, right? Which we are doing most of the time, right? What most of you or people working in mechanical plant or chemical plant, so what they do, so they time to time, because their daily job routine data, routine operational data, routine inspection, all these. So in a way, your purpose is to identify the hazards, and you are uh, evaluating the hazard may not become the disaster, right? So based on the first phase in integrity management planning, so what sometime you found that, okay, this modification to be done, one rep onto the pipeline to be laid. So that is the integrity management implementation, because from the finding of this you are implementing integrity management, mitigation, intervention, and repair, major thing, right? So if it is likely chances that, uh, for example, uh, uh, any like in the event of war these days, some refineries are being hit, right? So we, or 9/11, so the mitigation is that we have to, uh, if the new hazards are being identifying, so we have to preempt if this hazard will become available, so that the asset should be resist that, right? So we can do and learning and development. So as the knowledge, the defects are being improving and coming, the new technologies are coming, so learning and development is an essential part, right? So the enabler or driver, which are outside the cycle, in which it is company policy, how much uh, companies are allocating onto this maintenance and management, organization and personnel as a whole, reporting and communication. So at all level of your uh, asset integrity exercise, operational control and procedure, which are SOPs, management of change. So that should be also being considered, that the uh, people may be changing, but asset to be operating at in the same situation, contingency plan, audit and review, and information management. This is system is from by the DNV RP116. So that is clearly defined in that. So asset risk, uh, integrity management, like you can see in the picture, there is, for example, uh, in the middle, this is uh, related to the jacket substructure for offshore structure, like the platform, this uh, like tower kind of a structure, which is a steel structure, right? So that is being, for example, 20 years old. So fatigue, for example, the fatigue damages, right? So that you will get data from there, and then the structural analysis team, like this green color, right? One of the joint, right? They will do the analysis, right? And above over there, here, you can see this joint analysis, any relevant software, it is being uh, used, for example, and this joint, which is the part of the uh, overall tower. So the integrity and force distribution have, if you have strengthened this joint, and that what will be the impact on the global performance of the jacket structure, right? So here, as you can see in the middle slender, risk-based integrity management, meaning to say all these analysis, you have to estimate the risk, right? So you will be, in the end, you will be looking this risk is acceptable or risk to be mitigated, or computer aided for that. Some we use computer aided engineering, like finite element tool, as we have done, and inspection finding, which is risk based inspection. So little bit background of design engineering, right, which is in the conventional design approach, so which since beginning it is depending on to the maximum applied stresses should not exceed, as I say, the certain fraction of the yield strength. As we say that hoop stresses into the pipeline should not exceed, for example, zero point 0.6 Fy. Fy is the yield strength, right? So that is the elastic limit, right? So that it should not be uh, enter into post-elastic behavior throughout the lifetime. So the ratio of the, so this is, for example, sometimes as in older design, which were very overestimated design. So they were using safety factor of 3, meaning to say 600 megapascal. So people earlier using two design strength was 200, meaning to say you estimate the wall thickness based on if you are using 3. So that, and even those the over design have not proved the safer design and uneconomical, right? So the approach is based on the assumption that the component is free from any flaw and defect. The safety factor would compensate for any unexpected overloading or deterioration of the component during its service life. But now with the advanced computer analysis and advanced knowledge, so the much now like reliability based design and probability based design, they are being making structural design more safer and more economical, right? So this is like seesaw, right? You have to balance out yield strength, which is the capacity or resistance to the external load multiplied by safety factor, right? So that is the philosophy of the working strength design or conventional design principle, right? So in the maintenance and asset management and maintenance. So there are also implied engineering ethics, right? Because particularly at the organization level, sometimes it required, for example, could say at this stage, you have to do turnaround, you have to do the shutdown, right? So companies mostly they miss or they skip few of the turnaround, right? So, and that might be because if you can get the statistics of in industries particularly, so many industry failure, 70% of causes are the human error. Human error means to say which are where management decisions and knowledge of people and so on, right? So which are where uh, engineer, if organization go beyond the engineering ethics. So general duty of an engineer is to ensure that a facility at all time possesses integrity that is as responsibly practicable to protect the interests of health, safety, and environment, as well as the safeguarding the company investment. Right? So this is the these flow diagrams are the easiest way for understanding, right? So the design is one of the integral part of the asset management, right? So it involves integrity management process. It involves design, after design fabrication like pipeline, fabricating and installing, right? Then uh, database, which means that now commissioned and working. So database, which means this is your maintenance company, right? So uh, 10 years old asset, so 10-year data in a central repository that will include all the information, which means incidents, if anything happened, anything, any modification has been done, then this database, right? So that if you are doing, so 10 years history is there. So you can inspect, and with that inspect, you can re-evaluate, right, at this time. And then you can find out that if the integrity target are not being met for the next 5 years, so we can repair or retrofit of our structure. So in design or uh, all the time in operation, so the load will be there, right? So the load, there are variety of sources of load, which are external load, which are being applied on our asset. So, and the load are not in constant term, right? They are changing in magnitude, right? So our interest is most unfavorable load, which might be happen during the service life. So the unfavorable situations are translated in the form of applied load, on which are either gravity load, which are related to gravity, like self weight of the structure, people weight, other weight, which are related to the gravity, right? Weight. So environmental load, temperature, right? The ambient condition, seismic, flood, wind, right? Fabrication load during fabrication, right? So we have to apply some kind of loading, right? Installation, so hook up, hanging, right? Accidental load. So those are certain categories of loading that we have to consider when we design or maintain, right? So, so it is not only at this after design phase, with, as I have given you the example, right? When there will be corrosion, 20% corrosion, so we cannot put the 200 bar is the external load, which is being applied on the internal wall of the pipe by the flowing gas, right? So we have to limit the load to 180 bar as new evaluation, right? If or either we have to repair and maintain if we have to apply 200 bar. Accident, right? There are sometimes the pipe, particularly onshore pipeline, race pipeline, some collision may cause denting, right, and gouging onto the pipe. So that is the accident, right? This collision, vehicle collision to the pipeline is a kind of accidental load. As I say, the uh, loads are fixed load, which are dead load, and live load, which are variable, right? Which are not fixed. So dead load are deterministic, meaning to say, you know the physical properties and physical condition, which is volume, right? You can measure, you know the density, you can find. They are fixed, right? This table or chair for this pen, like its geometry and volume is not being changing, density is not changing. So it is so long, it is integral pen, right? The piece is not broken, so the weight of uh, pen remain constant, right? Live load are invariant. The wind, today wind is blowing fast, next day the wind is blowing slow, right? So these are stochastic, it is time depending, there is large variation, high uncertainty, so it can be not easily measured, so they can be extrapolated with the probability of occurrence. There are also code and standard and specification, like as so standard requirement for analyzing structural integrity, for example, old BS code, STM, American concrete, DNV, API, Petronas technical standard, and other governmental and operators requirement. So which as part of the integrity manager or asset manager, we have to comply and we have to have the knowledge of such code and standard. So if we can look oil and gas industry, so American Petroleum Institute, RP, which is recommended practice 2A, which is the naming of which practice. So 2A, it is related to recommendation for design and construction of fixed offshore platform, like first issued in 1967, blah, blah. So after Hurricane Hilda and Betsy destroyed 28 platform in Gulf of Mexico, right? So now uh, you have to have the knowledge if you are relevant to the platform and complying to API. So API RP2A for platform, but you have to look to the latest version, right? Because since 1967, so it has gone several times, it has been revised or modified. European Classification Society rules, like that's first issued in late 1960 after Sea Game disaster in 1965. So those are some evolution. So like you are in mechanical, so there are American Institute of Steel Construction specification, right, or American Society of uh, steel construction. So specification for design, fabrication, erection of a steel building, right? American Welding, Structural Welding Code, BS 5950. So these are some examples of the code which are being available. There are plenty of other codes, right, which we have to comply, we have to have the knowledge, and we refer time to time in managing our structure. So whenever we are looking a system, we are talking when integrity and asset management. So every asset is a composition of uh, several components, right? So in order to comply the asset integrity, so all component as a whole to also be integral, right? For example, if system 1 which has only one component, so it is easy to maintain because the whole system is composed of one element, right? So element integrity and system integrity. But system two, there are like three members, right, for this. So in that, if any one of the component is failed, so whole system is considered failed. So if all members are the same, which system has the highest factor of safety, right? That is. So what can change the integrity of an existing? So which means, as we say, that at the design condition, so or after 5 years, we say that the integrity conditions of pipeline have changed, right? So what has changed? So uh, if nothing went wrong but the code and regulations, right? Based on the information and knowledge assessment, court found that, okay, that safety factor, so this is the reanalysis because this might fail if this criteria happen. So time to time, a new addition of code come, and so now under the new addition of API RP2A, so we have to requalify our asset, right? Because a new criteria have been implemented and we have to check whether the new criteria will be complying. If not complying, so it is being considered that the asset is not on 100% integrity level because this criteria of the code is not complying. Improve refined loading estimate. So how accurately you can estimate the loading, right? So if poor estimate, that will affect it will decrease the integrity. Accurate estimation of load can give you better integrity. So modification, alteration, right? Damage repair, different use application, modification, wear tear, corrosion, aging effects, fatigue, extended, reduced service life. So those are the factors that will be uh, affecting or controlling the integrity of the structure. So there are also some code, they have given some allowances. And so this is an example of the allowances, right? So again, analytical technique. So like we are in digital technologies, as I said, this the computational method, AI that can change the integrity and knowledge, right? Because advanced method uh, of analysis of integrity are improving the confidence. So modification and alteration, addition, like beam design, column design, right? So plate stress analysis, beam local checks. So by doing so, we can add the aging effects like several material creeping, right? The creep, reservoir compaction, right? Like the well integrity, long-term differential settlement, like for the plant structure, right? That or the tank foundation, right? The storage tank. So the ground settlement uh, will cause the aging effects and reduce the integrity. Extended reduced service life, a structure that is designed for 1 in 100-year event, meaning to say the most critical wind condition, we will jump into 100 years data, right? And we design for the most critical, right? So with a design operating life of 25 years has 20% chance of experiencing the 100 years event, like return period and probability. Extending the operating life to 50 years increase the chance of experiencing 100-year event to 40. Longer will be the life, the chances of occurrence of the 100 years wind data, the you say from 1925 to 2025 data, it is showing that in that particular region, that is the maximum wind speed, right? So the if you are designing a structure for big service life, so chances of occurrence of that values will be more, right? Because longer span, right? So that's why bigger will be the service life, bigger will be the chances of occurrence of that 100 years return period, right? So reassessment when you are doing like reassessment of pipeline, as we say, for the desired operating condition. So they, so we need this information are important of the past. Date of design, when it was designed. It is, we are not interested the date, but we are interested during that date, what would be the condition and like what is the time period, how it has gone, right? And so on. The relevant design and material specification. So what was the design of assumptions, what material was used, what were their specification, and where are as-built drawing, right, which are important for the reassessment, design reports and calculation. So we have to access what assumptions the engineers made at that time, right? Why they made. So what was the design criteria? What was the design approach? Where were the calculation, right? So that we need design code use, right? And their addition. For example, API RP2A, which addition was used to design this structure. Environmental criteria, whether they have considered wind, what return period, 100-year return period, right? Soil data, because there is everything is resting and all load going to the soil. Tank, the big tank resting on foundation sending all the load to the soil underneath. So the properties of the soil where your asset is situated. So it is important, and foundation or footing detail, etc. So these are the information, or these are the data or uh, reports you have to have access onto that for the reassessment of the integrity of your structure. So reassessment steps establish existing condition. So after reassessment, so we develop new baseline, right? Because one baseline at the time of commissioning of the asset. But now, after 20 years, so new data, new assessment, the whole life cycle assessment you have done, reassessment, so new baseline you will be given. So date of install construction and erect and method as build drawing, fabrication, welding, material. So all these information is needed. So reassessment step, original design condition, which means at the time of design, we compare existing design condition, and if we do nothing, so future design condition. So original design condition 20 thick X65 pipe for this gas processing, which is running at 200 bar. Existing have some corrosion spot, that, so it can comply or it can just save for 180 bar. Future design condition, if next 5 years do nothing, so the what would be the safe operating condition? Maybe 150 bar, right? So that will be the purpose of assessment. So the steps, qualitative based on engineering experience and judgment. So qualitative assessment, like condition monitoring, right? You are looking, so most senior and experienced staff, so he can or she can identify, she can make hypothesis about the condition of the asset, right? And then first order analysis, simple hand checks. You can get some simple data and just simple checks, which we can do, right? In any engineering evaluation, right? So first order analysis using software, right? Like for oil and gas industry, for offshore platform, SSES, pipeline CSAM, and so on. So quickly we can run with this data. And the second order, which is the advanced, if we can find something fishy into the first order, because if straight away you go for detailed assessment, which was not required, so that will involve money, right? In detailed assessment, maybe you have to shut down your plant for 1 week, plus more manpower, plus more testing, and in the end, you found that, oh, asset can sustain these operating conditions very safely for next 5 years. So, which means that you have done an expensive exercise, right? Which the consequences cost you money because you lost this thing, and it concluded that in present condition, asset is fit for the next 5 years. So that the third block, first order analysis, the simple, quick software analysis will give you an indication whether it is risk at high risk, low risk, or medium risk. So determine acceptance criteria, because after reassessment, so what result will be acceptable, right? You can say on what basis, right? So you accept it. What is your benchmark, right? So either statutory requirement, right? The bodies say, HSC say, Dodge says, right? You can say if it is within the statutory requirement. Then there are also corporate requirements, right? Some corporate, like these days, they say ZETO, zero tolerance rule, or zero uh, uh, non-compliance rule, right? Zero fault rule, right? So for that, they have set up some minimum criteria. Acceptable level of risk, which you estimate the risk and you can engineering experience and judgment, and the criteria used may differ between global system and local system. So API RP2A working strength design section 17 process structure selection, pipeline, or like platform, which is jacket platform, categorization, under what category, sensitive load, high load, medium load, condition assessment, what is the current condition, design basis check, analysis check, the previous work, right? And consideration of mitigation. If you found that next 5 years it cannot be worked properly, so you suggest some modification. So, or mitigation options, right? If you are not doing now, so you can mitigate, so reduce load. So you can say that instead of running 150 bar, you can derate to 120 bar, 100 bar, right? So by doing so, you are reducing the chances of accident and so on. Change from manned to unmanned, right? Install marine growth, it is talking from the for the offshore structure, right? Install marine growth preventer, right? So there should be no marine growth next to your subsea structure and so on. Remove surplus appurtenances, right? Add additional member, guys, grout hollow section, joint, and reduce live load, limit box section. So now, as the philosophy are being changing, digital tools are available, we can implement advanced structural analysis techniques, which is structural reliability techniques, all data, and you put, I think you will do a subject on structural reliability, right? You will learn finite element method, plastic collapse analysis. Those can be used to find the most accurate reliability and integrity of your structure. So the decision, which is operating risk and safety, economy, and environment. So you have to make balance in between two, right? So again, for how much risk you can take, right? So as this balance is indicating that you can take the risk without jeopardizing the targets of safety, environment, and economics. Now we will see the reason why these major accident hazard. Right? So incompetency. Right? So as I said, uh, it is as company says that, for example, on this plant, right? So BE mechanical or BE Bachelor of Engineering in Mechanical is basic requirement, right? Must be recognized university and registered with Board of Engineers Malaysia, right? So that is being okay at the time of entry as fresh engineer, right? So fresh engineer will be like mentored by the senior in a group. After 3 years or after 5 years, so there are many things changing, right? In design rules, in the software system, and so on and so forth. But the engineer who was entered as fresh engineer in 2023 and 2026, he did not go or he was not sent to any short course or any career development exercise. So that is considered incompetency, right? Because uh, there are a more higher risk of making error in the design or integrity management. Inappropriate design, which is not correct, right? Design approach is more important. Like no identification of barriers. So barriers are protection, like in pipeline, even when a new pipeline, so it will be coated, it will be painted, right? So those are the barriers against the hazard, corrosion hazard, right? For example, or for fire hazard, so protection against fire, the plant which are coated by fireproof coating, right? Like intumescent coating and so on so forth. Assessment of process and safety management, absence of process and safety management. So haphazard, there is no SOP developed by the organization. So that accident may happen. Absence of integrity management strategy, absence of MOC, mechanical operation and control processes, maintenance, operational and control processes, operation outside the limit, absence of reporting, communication, and information management. So to minimize and operate the asset within alarm as low as uh, uh, practicable, as reasonably practicable, comes with the introduction to asset integrity management. So these are alarm principle, which means it talk about the risk. 1 in 100 risk of death from 5 hours of solo rock climbing every weekend. Meaning to say how this principle say what is the risk, how you define the risk. So the probability of failure is 1%, 1 in 100. Right? So that the risk when someone is a frequent going for rock climbing, right? So 5 hours of solo rock climbing, right? Every weekend or every weekend, somebody going alone without any assistance or company. So, and doing continuously 5 hours. So there is likely data statistics say if he went 100 weeks, so the chances are that as from the data, so in those event, right? So during 100 times went, so one times happened that he uh, dead, right? So this is considered the very high risk, right? So if 100 weeks, so if you are either stop or 100 weeks, so there are likely chances that you can die. 1 in 1,000, so little uh, risk factor has reduced. So risk of death due to work in high risk group within relatively risky industries such as mining, right? So the people working in mining, this risk are carrying 1 in 10,000. In 10,000 event, so one fatality, right? So risk of death in a traffic accident. 1 in 100,000 risk of death in an accident at work in the very safest part of the industry. And 1 in 10 million risk of death by lighting. Right? So this you can quantify your risk and you look what are the likely chances of fatality, right, due to the risk. So they have come that this risk, the frequency, one in this one greater than. So they have plotted in this. So and the severity level, right? Like 1, 2, 3 main. So catastrophic. Right? So the this is the uh, at warning. This is high risk. This is medium risk. Right? These two colors, which is purple and yellow, come under medium risk. Red is intolerable risk. If your asset is posing, so immediate action. I'm not sure some of you are uh, in Petronas, but those are even Petronas or Petronas operate contractor, right? Subcontractor, whoever involved in Petronas job. So apart from the other relevant standard, so there are also you have to comply to the Petronas technical standard, right? So there are the uh, standard which cover or talk about structural integrity. So PTS 50001, Manual for Maintenance Management Philosophy, right? So most of the engineers attached to the maintenance, they have to comply. 08, Asset Integrity Management, a strategy for the inspection of production facilities, and 14, radiographic inspection. So these three Petronas standards, they are being related to asset integrity management, or as part of that, structural repair and reliability and appraisal, right? So because a major chunk in any industry is engaged in maintaining the structure. And this is, there are other talking about ultrasonic and asset maintenance and management. Okay. So with that, it was uh, so then structural health monitoring and inspection and maintenance of a structure. So this is the next topic, right? Because health monitoring is part of integrity. Right? This topic covers the principle, aims, and purpose of structural health monitoring, how it is performed, what are its components, and the major benefits. So as my background is structural engineering, like this. So, and like Penang Bridge, right? So all the time now it is, I think, 40 over years old, the old bridge, right? The first. So when we go to the inspection as integrity assessment or health assessment in a way, So the major question is your structure telling you the truth, right? Looking at that physical inspection, right? So that is the big question behind you. So to find the truth of your bridge, because answer is that in your physical inspection, you can get the physical condition like a human being. We have a stomach ache. What is the cause? Right? So that is being done after ultrasound or this, that. So this is the question, is your structure telling you the truth? If structure is not telling, we have to find the truth. And that is the health, structural health monitoring. So definition in service evaluation of structural health status by measuring key structural and environmental parameters on a continuous base at real time, right? Not discrete, continuous, daily, weekly, monthly, or so on. Purpose of SHM. SHM is a common term used in engineering structural health monitoring. Detect structure damage, safety, provide maintenance and rehabilitation advice, improve design guidelines and disaster mitigation. So all these to avoid, so this structural health monitoring exercise is done. So regular inspection certainly reduce the level of uncertainty, but still presents important limitation, being limited to the observation of the structure surface during short time spaced by long period of inactivity. Principal aim, structural health monitoring aim to provide more reliable data on the real condition of a structure, observe its evolution, right? Because like sensing, continuous light, so that can give the evolution and detect the appearance of new degradation. Objective of structural health monitoring, performance enhancement, right? So because and confidence, right? Monitoring of structure affected by external factors, by wind, particularly windstorm, earthquake, flood. After flood, how the structure is behaving. Feedback loop to improve future design based feedback, meaning to say database as I have shown you one framework. So whatever every single piece of information should be residing into the database that will be the feedback loop for the future or management of change. Assessment of post-earthquake structural integrity, decline in construction and growth in maintenance need, but the move towards performance-based design philosophy, not the rigid, right? The performance target, if we have to analyze and as off condition as the same condition as now, if the asset is fulfilling the performance objective, so which means that the health is perfect at the moment for performing this function. So from there we can say the principal objectives are validating modification of an existing structure, assessing safety and performance of a structure affected by external work, tracking long-term movement, degradation of material in critical structure, providing a feedback loop, and assessing fatigue line, right? Long-term damages, checking novel system, of construction and new structural form, assessing of post-earthquake structure like ground structure, plant structure, building, bridge, enhancing effectiveness of resources as construction decline and maintenance need increase, catering for the move towards performance-based design philosophy. So by permanently installing a number of sensors, continuously measuring parameters relevant, for example, sensors on bridge, which will be tilt meter. So any movement and tilting or vibration sensor. So the real-time data collection, right? Those can be uh, 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 installed, stored into the centralized database. So instrumental monitoring is a new safety and management tool, or even now fiber optics, right? That ideally complement traditional method where you go either physical inspection, then some kind of NDT. But these sensors are permanently installed, right? And transmitting the data. Monitoring even allows a better planning of the inspection and maintenance. So you can only go to the physical inspection and testing when your sensors are pinpointing a critical condition. So fundamental hypothesis of structural health monitoring. So there are when you find your finding, so you can make certain hypotheses, right, which are hypothesis one, right? It is your mindset, why you are doing, right? Why you are looking. All materials have inherent flaws or defects. Right. So there is no such perfection. So if you will be performing with that mindset, right, and you are installing, because you are installing sensor for continuous monitoring, right? So question will come that will incur cost, but cost for what, right? So what is the benefit of this cost? So if your mindset is telling there is none of the material which is flaw free. So, and this is very critical bridge like Penang Bridge. So for the safety of a structure, I need continuous monitoring, right? Because I need where are those flaws. Hypothesis 2, the assessment of damage require a comparison between two system state, meaning to say, right, so any crack, any other anomaly you find in your structure, in your system, right? So how you to make decision, right? So you will be comparing with contemporary defects and their consequences which have been testified. So you can compare with that where your finding are lying, right? So comparison. Hypothesis 3, identifying the existence and location of damage can be done in an unsupervised learning mode, but identifying the type of damage uh, present and the damage severity can generally only be done in a supervised learning mode. Meaning to say, the existence and location of that somebody say, okay, I have seen the pipeline at along North-South Highway at 150 kilometer milestone. So it is there. So that anybody can do, right? Unsupervised, right? Learning mode. But for identifying, so somebody layman can say there is crack, there is bend, there are dent on the pipeline. But what is the severity? Right? So that can be testing and all are being done in supervised manner, and this data is being analyzed by in supervised, meaning to say expert uh, supervision, and he can identify not everybody, right? That's why there are requirements for this minimum, like in Malaysia, professional engineer, IR, hypothesis for a sensor cannot measure damage. Right? They give signal. Those signal we can interpret, right, from the calibration data. B, without intelligent feature extraction, the more sensitive a measurable measurement is to damage, the more sensitive it is to changing the operational and environmental condition. And the last, the length and time scale associated with damage initiation and evolution dictate the required properties. So if propagation is slow, fast, right, so that will indicate the material property. Yeah, one more, sorry. So there is a trade-off between the sensitivity to damage of an algorithm and its noise rejection capability. The size of damage that can be detected from changes in system dynamic is inversely proportional to the frequency range excitation. So those are the hypotheses or belief in structural health monitoring. So these are the component. Structural health system include structure itself, sensor, which we will be installed, data acquisition, because sensor are sending signal. So that is in the form of data. So that your console will be collecting, and then it will be analyzing and store, transfer and store, and then data management for the lifetime. So data interpretation and diagnostic is more important. Just same thing like uh, somebody went for like lab test, like a radiological test or this test, right? So those are the expert who can perform the test, but the test report are sent to the doctor, right? He is the expert who interpret, who diagnose. So the that required system identification, structural model update, right? For that purpose, structural condition assessment, prediction of remaining service life. An example of this technology is enabling sensor in a structure like bridges and aircraft, right? So after every flight, so all the sensor data are being reviewed, and anything weird is observed, so it is being sent to the next expert. So these sensors provide real-time monitoring of various structural changes like stress and strain. In the case of civil engineering, structure, the data provided by the sensor is usually transmitted to a remote data acquisition center. I think the same thing in civil engineering example, because most of the projects are in remote area. With the aid of modern technology, real-time control of structure, active structural control based on the information of sensor is possible. So the step determination of that damage existence, what through there, the system which are working which receive data and they convert, translate, evaluate, interpret. So these are the step: determination of damage existence, determination of damage geometric location, quantification of damage, severity, and prediction of remaining life of the structure. How to do SHM in practice? Visual inspection first, fully experience based, meaning to say it is being done by experience people, and subjective, non-quantitative. Non-destructive evaluation, which is without what uh, damaging, right? So uh, uh, we have to do like ultrasonic and all. So various technology for different purposes are there, demands a high degree of expertise, right? Because it is like X-ray. So chest X-ray, not everybody can interpret, but usually doctors are experts, they can interpret. Time consuming and costly, usually require a priori knowledge of potentially damaged region. As one of the hypotheses say, we should have to have some comparison, right? Or the previous example where we can interpret works only in accessible region, right? Not everywhere we can apply. Interruption and downtime are possible, labor intensive and risky. Current safety assurance practices, design with large safety factor over design, design for damage tolerance like life prediction, material damage, fracture, quality control, accurate specification, and periodic inspection, manual, non-destructive evaluation, and why do disasters happen? Because of design uncertainties, loading conditions, so particularly random loading, wind, earthquake. So in that, a lot of uncertainties involved, manufacturing uncertainties, fabrication process, analysis process, right? So as competency is not that high, so we can material variation, so not consistent material quality, environmental effect, aging infrastructure like spacecraft, airplane, the plant, and so on. Conventional structural system, very dumb, designed to achieve set of intended function under pre-selected load, large safety factor is employed, unable to adapt to structural changes. So those were the rigid, like in this you can see in the same Japan, right? So now in even severe earthquake, most of the structure sustained because SHM or the knowledge of maintenance have improved compared to past when all such failures happen. So the future now, which we are talking in this, so the future is smart structure, right, that are able to sense and response, adapt to change in their environment, right? Like self-healing material, right? Which will be self-heal, right? So characteristics of a smart system integrated with many sensors and control device through information network to achieve an enhanced performance at a reduced life cost, right? Like this is some bridge of 21st century, how they are being maintaining. So this is all a smart system, right, with our 24-hour sensing. Biological analogy to smart structural system, so which is like information is in our brain, which process, we sense our veins, our sensing, right, feel, right, visual, hearing, right, like macro sensor, the actuator, like our hand, finger, muscles, right? So that on a same system, right, we have developed the structural health monitoring, right? So like this is simulating to this, like this in building. So various sensors which are simulating to the human being and the brain for storing data. I think few slides I can discuss. So the component of a structural system, so like in Bubble, a smart structural system, so which means network sensor, uh, which are being uh, connected to the network and continuously sending the data information processing. So what signals come from the uh, sensor, so it will be processed, right? And then uh, control and actuator. So if processed, after that there are alarm or some control system, so that will be an structural system. Right? So a smart structural system is roughly defined as a system with sensor, data processing, control and actuating device, and therefore is adaptive to the change in extreme operational condition. Right? So rather than you go, so the protection will be on when the through control the signal will come and to adopt the safety measure, like in case of earthquake and so on. So this is the system diagram. So we have brain, which is computer, right? Prognostic and maintenance scheduling based on that. It is much easier. It is much safer and timely, right? Benefit, better safety, cost saving, at cost of inspection, 40% saving on airplane inspection, right? Because immediately, and it is better early detection of any anomaly, autonomous damage detection for disaster mitigation. So monitoring help to save in many ways, allow structural management, monitoring ensures long-term quality, and monitoring discover hidden structural reserve, right? It is not only if it is hidden reserve. Monitoring discover deficiencies in time, reduces uncertainties because continuously and increase safety, and monitoring increases knowledge because new anomalies coming and which we can apply fundamental theory and come to the conclusion. So currently we have seen aerospace in discipline was the first, right? For aircraft safety, they have come. So they are using this SHM and airframe, which means the structure of aircraft engine component, right, composite material, etc., civil structure, because they are critical, bridge, dam, skyscraper, earthquake impact, mechanical system, bearing, engine, and so on. So now I think SHM, so structural damage. So I stop here, and I think next, whether I have added some slide or no, I will add few slide on AI in SHM, right? Which is some part is there, right? So so yes, so slide 150, I think, right? So yes, 150, 151. So next week we will continue, right? So any question? Any question?
None from me.
Okay, thank you.
Okay,
Thank you,
Doctor. Thank
Doctor.
you.
Thank you, Doctor.
Okay, thank you.